Hello students, welcome to Design of Steel Structure. In this session we will cover built-up column. So before going to detailed discussion of built-up column, we should understand what is built-up column. So built-up column is something where we use more than one standard sections. The sections may be two channel sections, four angle sections. So it depends on the requirement. Okay, basically where only one standard section, is not sufficient to carry the required amount of compressive load, then we should go for using two standard section as a one unit. Okay, so then using these two standard section as a one unit is called a built-up column. Like here in this picture you can see there are two channel sections. This is one section and this is one sections. These are at a spacing of something. Okay, and these two columns are connected by this inclined flat plate or inclined flat bar, you can say, and this is called lacing. Okay, this is called lacing. So this lacing connects or binds these two channel sections, okay, by bolting or riveting at these points. Okay, so these total column acts is called a built-up column. Built-up column means here we have used two channel sections back to back, okay, by connecting these two channels by a proper lacing system. Okay, now there is a second picture you can see. Here also they have used two channel sections. This is one section and this is one section. These are connected by this lacing system, and this is like double lacing system, because here there is one lacing system and in cross orientation there are other lacing systems. So this is double laced built up column, and the first figure it is called single laced built up column. Okay, so built up column is required when only one section is not sufficient, because suppose in this channel section, in this column, the required amount of load, suppose which is coming from the top, that is equal to like P, and if you use only one channel sections, this, and if we apply this compression load on this channel section on the top, okay, it may not be sufficient. Okay, so in that case we should go for built up, okay, by assembling two standard sections or four standard sections like that. Okay, so now the next point which you should understand, that is, if we use only one section, okay, these several sections, so there you can see there are two axes. Okay, so there will be two axes. One will be, okay, let me draw another picture here. Okay, so here in this channel section there will be two axes, right? So one along this axis and another is along this axis. So this point is the CG point. Okay, this is the CG point. Now this section, let me say that this is Z axis and this is Y axis. So here in this section, if you see for particular channel section, you can see that RY is less than RZ. Okay, so if Ry is less than Rz, that means slenderness ratio about y-axis will be more. Okay, so so if this column or the channel section fails, it will certainly fail by about this y-axis. Okay, then if it fails about this y-axis, then this is called total failure. Okay, but before failure of the y-axis, it will not fail about this z-axis, because z-axis is a stronger axis, because rz is more, so slenderness ratio about z-axis is less slender about z-axis. So if it fails, it will fail about this y-axis only. So when I'm saying this, it is failing about y-axis, you have to imagine that the rotational axis will be the y-axis. It will buckle in such a way that the rotational axis will be the y-axis. Okay. Now in this case, as ry is very less than the rz, so y-axis is the weaker axis. So so when the compression load is maximum or greater, in that case this type of column will fail about this y-axis. So what will be the alternative arrangement to use to carry that required amount of load? So we have to go for the built-up column. Now whenever you are going for built-up column, what is your concern? What should be your concern? That should be increasing the strength. Okay, now in this channel section, the RZ is a stronger axis, so there is no problem with the Z axis. So only problem is about Y axis. So we have to increase the strength about this Y axis. Okay, so if we place these what I can say, another angle sections, or sorry, channel sections in these directions. Okay, like this. So let us say this is same angle section placed back to back. Okay, so in that case the z-axis is becoming the same, is remaining the same, but here, because this z-axis is passing through the CG of these channel sections, so it is symmetric about this z-axis, so it will be same, right? But for the second section, the CG line is this. So for this left hand side section, the CG line, or the center of gravity line about this y-axis is this one, and for the right side section, this is this one. So if we use these two channel section as a built-up column or as an assembly, then the new center of gravity will be found by this. So this will be the new center of gravity. Okay, so y-axis will be shifted, because there is two standard sections, and due to this arrangement, the y-axis will be shifted to the center of these two channel sections. Now by making this arrangement, we can increase the radius of gyration about this y-axis, because the axis about this z-axis, okay, is not changing. This z-axis is not changing. Location is z-axis is same, but the y-axis is changing. That means the moment of inertia about y-axis will change. If the moment of inertia is changing, that means we can say that the radius of gyration will change about this y-axis. So our target will be to increase this radius of gyration about this y-axis. Okay, because radius of gyration about z-axis will remain same, because z-axis is not changing, only y-axis is changing. That's why the radius of gyration about this y-axis will change, and it will increase certainly. Okay, because the here in this case, if we need to find out the moment of inertia about this new axis, this is the center, this this one. Okay, that will be moment of inertia of these two channel sections. Okay, iy plus iy plus 2 into a plus h square. This is h, and also this will be h, because this will be the center point at the center point. So this is actually h, and this is also h. So moment of inertia about this new axis will be iy 2 into iy, because two sections are there, plus 2 into a h square. Okay, because two sections, that is why it is 2a and h square. This is basically from parallel axis theorem. You might have studied this topic in the previous semesters. Okay, so this will be the new moment of inertia about this y-axis. I y, you can say this is I y dash. Okay, now, so basically what we are doing, we are increasing this radius of gyration about this z-axis by 2 times, and we are increasing the radius of gyration about this or moment of inertia about this y-axis by this equation. Okay, so if we are increasing this moment of inertia about this y-axis, we are increasing the radius of gyration about this y-axis, becoming that makes it more stronger about this y-axis, right? So now what I was saying, so in this type of column or compression member, only one section is not sufficient. That's why we have placed at a spacing, okay, two sections at a particular spacing, and they are connected by the lacing system. Okay, so thereby increasing the radius of gyration about this y-axis. Okay, that means we are reducing the slenderness ratio about this y-axis. Okay, so you have to understand this very carefully, because this is the concept behind this built-up column. So if you don't understand, then you should rewind this video lecture, and you should understand this first, then proceed to the next part. Now now let us understand the steps. Okay, so this PDF is made from the SK Duggal book. You can see it. Okay, so there are some guidelines or design steps, and these are mentioned in the IS 800 also. If you go to this 7.6, clause number 7.6 of IS 800, page number 48, you will see that there are a lot of guidelines, and these guidelines are basically mentioned in this point 7.11.1 of the SK Duggal book. Okay, so you can read it from the IS 800, or you can consult with this book. Okay, now before going to the discussion of these steps, what will be your problem to solve what will be your problem to solve this question? So you will be facing that there will be particular amount of compression load that should be carried by compression member. Okay, and you have to find what you have to find the required section and also the required spacing, because you can see there are two this is single lacing column, so one particular amount of load will be given. Okay, that load should be carried, and you have to you have to design that column. That means you have to find the required sections, and you have to find the required spacing between these two channel sections. Okay, and also you have to find this lacing plate, lacing bar, what should will be the thickness of this lacing bar, width of this lacing bar, and also what will be the inclination of this lacing bar. Okay, so that these points you have to design. Okay, so before starting, you will be having the particular amount of load. Okay, you have to start from that load. Now, to find the required section, you should assume the design compressive stress, because load is equal to design compressive stress into the area. Okay, so the load will be given, so load by the design compressive stress, which will be assumed, that will give you the required amount of area for the section. Okay, so here you will get the required area of the section. Okay, that area will be the area of the two sections. If it is a two channel section, then this area will be the total area of the two channel sections. Okay, so first step is design compressive stress is assumed, and it is guided that it should be around 125 to 175 MPa. Okay, for Fe 250 MPa steel. Now, if this is design compressive stress, you can find the area, that is A is equal to Pu by assumed compressive stress. So this is cross sectional area in millimeter square. Okay, So this will be the second step, and this area will be the required area for the whole section, not a single sections. Okay, if you are designing for 4 angle section, then this area will be the area of the 4 angle section. If you are using 2 channel sections, so this area will be the area of the 2 channel sections. So yep, you can find the area of one particular section if you know this total area, right? So you can find that area of the one particular section if it is channel or if it is the angle section. Now if you know the area of one particular section, standard section, you can go to the steel table. Okay, there you can see roll steel channel sections are given. Okay, in page number 16 you can look for that area from these tables. Here you can see there is a sectional area, so look for this particular area, and that corresponding to the area you will get a particular sections. Okay, so you choose that section. Okay, now now choosing the particular section is not uh, enough at this point, so you have to again check whether this uh, section, okay, this built up section will carry that particular amount of load or not. Okay, so because we have assumed this design compressive stress. Okay, so this is assumption. Now if we know the particular section, standard section, then you can find the exact capacity of this particular section. So again you have to check whether this section is becoming sufficient or not. Okay, so how can you check that? You can find the slenderness ratio of that member, and also you can find the buckling curve. Okay, that means I am saying this about this this buckling class. For channel section it should be buckling class C. So for that chosen section, you will know that the slenderness ratio will be how much. Okay, this you know, and you know this 250. Okay, then you can find the exact design compressive stress. Okay, so you have to choose this column and you have to use this KL by R. Okay, and you have to find the exact design compressive stress, and from that exact design compressive stress you have to find the load carrying capacity, exact load carrying capacity of that section. That means exact load carrying capacity will be FCD into the area. Now you know the exact area. Okay, so you will get the exact load carrying capacity that should be more than the load which will be coming on that compression member. Okay, if it is less than this external load, that means you have to go for the next higher sections. Okay, now here you see you have to use this class C because channel section comes under this class C. Okay, so this is the another steps. Now how can you find this slenderness ratio? There is a guideline. So how can you find this slenderness ratio for the this built up column? Okay, so the guideline is the effective length. If you read this, effective length of the column is estimated and the slenderness ratio is determined. The effective slenderness ratio KL by R in suffix E of the laced column should be taken as 1.05 times KL by R overall. The actual maximum slenderness ratio in order to account for shear deformation. So you can see for a column, uh, this last column, there will be shear deformation. That means there will be some this load. That means load will be coming from the transverse side also. That will induce some shear deformation in this transverse direction of the column. Okay, so to account for this, you have to increase this slenderness ratio. That means we are reducing the strength. Okay, so considering this point you have to find this slenderness ratio and this design compressive strength from table 9c. Okay, and you have to check. Then the next point is how can we find the spacing. Okay, so what I said in this here, we have to place this channel section in such a way that we can increase this radius gyration. Okay, so to what extent we can increase, so we have to maintain that this increment of this radius of gyration about this y-axis will be equal to the at least equal to the rz. That means moment of inertia about this y-axis will be equal to moment of inertia about z-axis at least. That means I y dash can be more or equal to this I z dash. Okay, so that point you should be careful. Now next is point 8. So what should be the angle of lacing bar? Lacing bar, you know, so that angle should be 40 degree to 70 degree. Okay, and the spacing of the lacing bar A1 is calculated. So what is the spacing of lacing bar? So this what I am discussing on these points, these are the steps. This after discussing these steps, we will go to the numerical. Okay, so what is spacing of the lacing bar? So spacing is means this is the lacing bar and this is also lacing bar. So spacing is basically this. Okay, from this point to this point. This is A1. Okay, so you see A1 spacing of lacing bar is calculated, and you have to check this point number 9. Okay, in this point number 9 it is mentioned that A1 by Ry is not greater than 50 or 0.7 times the slenderness ratio of the member as a whole. So you have to check it should satisfy these conditions. It should not be more than 50 or zero point 0.7 times the slenderness ratio of the member as a whole. Okay, now you should know how can you find this A1. Okay, this Ry will be the previous Ry, not the changed Ry. Okay, and after that, so up to point number 9, this completes the first part of the numerical of the problem. Then you have to design the lacing bar. Okay, so how can you design the lacing bar, that will be discussed on the next video lecture. What should be the parameters, what is the guideline of IS 800. Okay, now uh, we should finish this second video lecture. After that we will go to the numerical. Okay, and I will suggest you to read these points. That means point number 7.6. I think 7.6 of the laced columns. You should read these points. These are mentioned. The important points are mentioned here. Okay. What should be the thickness of the lacing bar, and what should be the width of the lacing bar, and um, what should be the that means slenderness ratio of the lacing bar. All these, and what will be the force on the lacing bar that are mentioned in these guidelines of this IS 800. So you should consult these 7.6. Okay, so we'll continue from the point number 10 on the next video lecture, and try to understand uh, these points what I discussed here. This is very important points to understand, because if you don't understand, then you will be solving these numerical as a robot. Okay, so you should understand these points. Thank you very much.